Okay, so thank you for continuing with us. So we're continuing to work with the intersections of planes and planes with lines. And it's important to recognize that if you've got two planes and their normal vectors are parallel, then those planes are either parallel or they're coincident. So either they're the same plane or planes occupying the same 3D space, or the planes are parallel and non-intersecting. Otherwise, the two planes will intersect in a line. I have two planes, they'll intersect in a line. And that line of intersection will have a directionality that is normal to the normals of the two planes. So if I look at the directionality of the line of intersection, right, if I want to figure out, hey, what's going to be this directionality of the line of intersection, it's going to be perpendicular to my two normals, right? So I can use technology or algebra to find that line of intersection, and crossing the normals will give the directionality of that line of intersection. Okay, so let's look at how we can work with these ideas, and then we'll move on to three intersecting planes. So let's say that we have three planes. Okay, so these three planes, which two planes are parallel? Well, let's look at their normal vectors. All right, let's look at their normal vectors. And we'll notice that plane 1 has a normal vector 2, negative 3, 5. Plane 2 has a normal vector 1, 2, negative 1. And plane 3 has a normal vector 2, 4, negative 2. All right, so because our directionalities between these two planes are scalar multiples, and if we look at the constant is not a scalar multiple, we know that plane 2 is parallel to plane 3, right? And the reason, our justification, like we said, is because the normal vectors are scalar multiples of each other. Okay, so there we are. Now I'm not sure why I lost some of my text, but let's go ahead and try and reload this. And so not sure what's happening, but we'll go ahead and rewrite what we have. All right, so we said that if we looked at plane 1, plane 1 had directionality 2, negative 3, 5. If we looked at plane 2 had directionality 1, 2, negative 1. And if we looked at plane 3 had directionality 2, 4, negative 2. And so we know that we were going to be parallel because the normal vector for plane 2 is equal to some scalar multiple of the normal vector for plane 3. Because that's true, we're parallel as long as the constants are not the same scalar multiple. Okay, not sure what happened with my technology there, but we'll continue. So what if we had three planes? Well, three planes, we could have a single common point of intersection. When this happens, the determinant of the 3 by 3 system of equations is not zero. And the system is said to be consistent and singular with a unique solution. All right, so it's important to understand that terminology. And M is the matrix of the coefficients. All right, if the three planes intersect in a line, as we see over here, then the determinant of the 3 by 3 matrix of coefficients is zero. The system is still consistent because there are solutions, but with an infinite number of solutions, and it's called non-singular. It is not a singular solution. Or we say it's consistent and dependent, that my variables depend on each other. Of course, if the three planes do not have a common intersection, well, then the determinant of the matrix of coefficient is also 0, right? So like we see over here, no common point of intersection, no uh, common point at all between the three planes, just between two planes. This means that if you know the determinant is 0, that's not enough. That's not sufficient to know if you have a consistent non-singular system or an inconsistent system, which has no solutions. So let's see how this can work. So here we have three planes described by the equations below. We want to determine the geometric relationship between the planes. If the planes intersect, we want to provide the point of intersection or the vector equation of the line of intersection. So one approach that we can use is our matrix approach. With our calculator, we can do our matrix of coefficients and set that up. -5, -2, -11, 1, 11, 6, 37. Right? And if I look at my row reduction, let me go to my toolbox, come down to matrices and vectors. Let me go to matrices further, and I'm looking at the reduced row echelon form. Back to my toolbox, and let's enter in this matrix of coefficients. So we have 2, 4, 3, and 20. All right. Then we have 1, -5, -2, and -11. And then we have 1, 11, 6, and 37. All right. So if we do that row reduction, we get 1, 0, 1/2, and 4, as well as 0, 1, 1/2, and 3, and then we have 0, 0, 0, 0 on our final row. So therefore, because of this, we know we have a line of intersection, right? That if we get a row of zeros, this is going to be a line of intersection. If we have zeros and then with a constant, we know that that's going to give us no solution. And we're going to figure out how we can approach that in a variety of ways. Okay, so the planes do intersect, right? And they intersect in a line, so we want the vector equation of the line of intersection. So that vector equation is going to be R equals, right? And if I look at this column here, that's going to give me coordinates of a point on the line of intersection, right? And then plus my parameter. And if I look at this column here, that's going to give me my coefficients. That's going to give me my coefficients in relation to my variables. And so if I were to solve this, remember that we'd be able to say, hey, x is equal to 4 minus 1/2 z, and y is equal to 3 minus 1/2 z, right? And z is just going to be our quote-unquote free variable. So I can say I have -1, -1, +2, that I have a 1 to 2 relationship for my directionalities. And there I have my vector equation, right? And make sure that your numbers are clear to read. So if we get a row of zeros, line of intersection. If we get a row of zeros and at the end a constant, no solution. Okay. Could we have done that on our calculator using the equation format? Sure. But notice that it asked us to determine, so how are we going to be showing our work, right? We can't really show the work if we don't write it down in that matrix form. There are other methods, but we can't just have it on the calculator. But let's go ahead and show you on the calculator how we could approach this. All right, so we have our first equation on the calculator, solving our systems. All right, then our second equation, x minus 5y minus 2z negative 11, and then let's add a third equation for our planes. We have x 11y 6z and equals 37. All right, and so let's go ahead and solve our system, and we'll notice that we have that same relationship of negative 1/2 to t. If I multiply everything by 2, that would be -1 to 2. Okay, let's go ahead and reset that. So let's look at our next question. Determine the values of the real parameter m so that these planes intersect in a point. All right, remember, if my determinant is not 0, then I have a singular unique solution. I'm consistent that I have a solution, but it is going to be a singular solution. So let's go ahead and look at my determinant when I look at my matrix of coefficients. So I'm really just concerned with the normal vector. So that's 2, -3, -1, 1, 5, 2, and then 4m -4. Okay. If I look towards this determinant, I'm going to have 2 times -20 minus 2m. And if I continue with that, I'm going to have a positive 3, all right, -4 minus 8, and then -1 and m minus 20. Okay, so that gives me together -40 minus 4m, right, and minus 12 minus 24, right, and then minus m plus 20, and that cannot be 0. So if I count up my m's, -5m. If I count up my constants, I have -40 and positive 20, so that's going to be -20, -12 and -24, that's going to be -36, so that can't be 0. So therefore 5m cannot be -56. And so if I want to intersect in a point, let's come back, right? If I want to intersect in a point, right, I know that I want to not be equal to 0, so m cannot be -56/5. Okay? I know this was a non-calculator question, but we can look at using a calculator to help us figure out that determinant. Go to my toolbox, come down to matrices and vectors, right? Go to matrix, looking at a determinant, right? And then back to my toolbox, and I'm looking for the determinant of 2, -3, -1, with 1, 5, 2, and 4. Well, what are we going to do with that m? And that's where we're going to have an issue in trying to use our calculator. All right, but let's go ahead and put in -56/5. All right, and then let's put in -4. See what happens. And we look and we say, oh, hey, that determinant would be 0. And we don't want the determinant to be 0, so we don't want -56/5. What if instead I had -56/2? You'll notice that it's a non-zero determinant, so that would be okay. So it is important to remember that relationship with determinants to understand unique solutions. Okay. And lastly, without a calculator, let's determine the geometric interpretation when this particular system does not have a unique solution. So let's look at my first part. For my determinant, I have 2, 1, negative 1, 1, 1, negative 3, 1, negative 1, k. If I consider that determinant, right? If I consider that determinant, that's going to give me 2 times k minus 3, negative 1 times k plus 3, and negative 1 minus 1. All right, so that's 2k minus 6 minus k minus 3 plus 2. So that gives me a determinant of k, and I have minus 9 plus 2, so k minus 7. So therefore I know I have no unique solution if k is equal to 7, right? Because that would make my determinant be equal to 0. However, I know that I'm not going to have a unique solution. I need to figure out what the geometric interpretation of that is. Well, there's a nice way using determinants to do that exact thing, right? That I can come over here and now I'm just going to swap columns. I'm going to do a column swap to move my z column to the constants and the constants in, right? And so if I consider that new matrix, that's going to be 2, 1, negative 2, right? Or 2, 1, 2, excuse me, if I just swap my columns. 1, 1, 1 if I just swap my columns. And 1, negative 1, 4 if I just swap my columns. If I find this determinant, right? If I find this determinant, that's going to give me 2 times 4 plus 1, negative 1 times 4 minus 1, as well as 2 times negative 1 minus 1. So that's 2 times 5 is 10. Negative 1 times 3 is minus 3. And 2 times negative 2 is minus 4, so that's equal to 3. All right, so because it's not 0, therefore we have infinite solutions. Right, we have a line of intersection. Okay? So that's a very interesting, quick approach that we can use. We could also certainly do row reduction and do those types of things if we wanted to. But what this determinant approach gives us is it gives us a way of knowing, hey, if k is 7, we're going to have an issue. If k is any number other than 7, we'll have a unique solution. But if k is 7, we don't know if it's going to be unique, we don't know if it's going to be an infinite number of solutions if k is 7, or if we're going to have no solution whatsoever. But if we do a column swap and we get a determinant that is non-zero, that tells me an infinite number of solutions. If we get a determinant that is 0, that tells me that there is no solution at all for that system. So an interesting piece. All right, and once again, be familiar with how to use the calculator, using determinants and computing things. You're going to have to be able to do things without a calculator. You're going to be able to use a calculator at times to be more efficient in your work. But that looks at intersections of 3 planes. You'll get more practice with it, but we know we could intersect at a point. The determinant is 0, is non-zero, right? So we know that in this case, the determinant is not 0. In this case, the determinant is 0. And in this case, the determinant is 0 as well, right? But if we did a second determinant, we'd be not 0 if I intersected in a line. And if we did our second determinant, we would be equal to 0 if I had no common point of intersection. Thank you very much for your time. We will continue with our work.